In our second video for proofs, we're going to focus on coordinate proofs. We've got two examples here. So remember, coordinate proofs means we're just taking a coordinate grid, using our points, finding out some information about those points, and using that to prove one thing or another. So in this one, we need to determine if these two triangles, J, K to L, and R to Z to T, if these two triangles are congruent to each other. We need to show and explain all work. Now, I know you don't have a whole lot of space or area on your page, so maybe write out like two, maybe three of these kind of pieces of work. On a test situation, you would have to show all of your work. Okay? What I want you to write down at least, though, put down you will be using the distance formula, and if you need to remind yourself, this is the distance formula. Square root of all of this, our second x term minus our first x term, all of that squared, plus our second y term minus our first y term squared. So x1 and y1 match up, like this point or this point. They have to match at the point. x2 and y2 match up, like this point here or maybe this point here. Okay, so you literally just plug all that into your distance formula. For this one, we're going to be using the distance formula to show whether or not these are congruent to each other. Okay. On the side somewhere, I want you to write down the position of each of those points. The spot J is at the point -4, 4. We go back 1, 2, 3, 4, and up 1, 2, 3, 4. -4, 4. K is at -7, 1. L is at -3, 0. R is at 2, 5. T is at 5, 2. And Z is at 1, 1. Okay, so that's just kind of the points for all of these. This information, these point values, remember these are all of our x values, these are all of our y values. We will use that in our distance formula while we're proving that. Okay, so I'm going to draw this one over, bring it up. This is the work you would show to find the distance or the length of JK. This length right here, start with JK, and I just plug it into my distance formula. Okay, -7, which I got from K right here, minus -4, which I got from J right here. All of that squared plus 1, again, I got that from K. Notice that 7 and 1 are first. They're the ones from K. Minus 4. Again, 4 came from J. The two red ones match from J. Two blue ones match from K. 7 minus -4. Remember, minusing a negative would be like adding a positive. So -7, sorry, plus 4 would be -3. 1 minus 4 is also -3. -3 squared became 9. -3 squared became 9. So I have the square root of 9 plus 9. 9 plus 9 is 18. So I'm looking at the square root of 18, which is about 4.2. So up here, I want you to write all of these distances down. J to K is the square root of 18, which is about 4.2. Okay, if you write down both, that'll kind of ensure that you have it correct. Square root of 18 is a little more exact. That's for sure exactly what it is. Around 4.2, that's rounding to an approximate decimal. Okay, so this was the work for J to K, so I'm going to move that one aside. If we're looking at from K to L, here would be our work. Again, just plugging everything into the distance formula. In this case, L is our last point there. So we started with L, -3 and 0 from right here. -7 and 1 from K, our other now red ones. -3 minus -7. Remember, that's like adding 7. So it became 4. 4 squared is 16. 0 minus 1 is -1. Squared, so -1 times -1 is +1. 16 plus 1 is 17. Square root of 17 is around 4.1. So from K to L, that distance is about 4.1, or exactly the square root of 17. Okay, so that's two of our distances, or at least two sides that we know. Let's get the last side of that triangle. L to J, again, I just plugged everything into my distance formula. -4 minus -3. Remember, that's like adding, became -1 squared from before. -1 squared is 1. 4 minus 0 is 4. 4 squared is 16. 1 plus 16 is 17. So I'm using the square root of 17, which is about 4.1. Okay, and this makes sense. If we look at our triangle here, they look like they're all pretty close in size. They're not exactly the same size, but they look like they're pretty close. This one, K to L, is exactly the same as L to J. So actually, I can draw that on here and say this one is the exact same size as this one. Okay, so we've got 3 of our side lengths kind of determined. Let's look at our other triangle then. If we look at from T to R, so going here to here, again, just plugging everything into our distance formula, 2 and 5 that we got from R, 5 and 2 that we got from T. 2 minus 5 is -3, 5 minus 2 is 3. Both of those, either -3 squared or +3 squared, will both end up at 9, because -3 times -3, negative and negative is a positive. 9 plus 9 is 18. Square root of 18 is around 4.2. So in this case, again, from T to R, they're both 4.2. Now, what I can do with that information is say that, whoops, I want 2 there, is the same as that. We know for sure that those are exactly the same length, because we just proved it using our distance formula. Okay, moving on from there, let's look at some of our other sides. R to Z, this here. Again, using Z, 1 and 1. R, 2 and 5. 1 minus 2 is -1. -1 times -1, or -1 squared, is +1. 1 minus 5 is, oops, this should be a -4. I'm just going to draw that in here. -4. -4 squared is still +16. +16 and 1 added up make 17. So square root of 17 is about 4.1. So the length RZ, that distance, that side, is about 4.1. Or we can say it is exactly square root of 17. And from Z to T, that one was hidden down here. Going from Z to T again, I'm just plugging everything in. 5 minus 1, 2 minus 1. 5 minus 1 is 4, 2 minus 1 is 1, 4 squared is 16, 1 squared is 1, 16 plus 1 is 17, square root of 17 is about 4.1. So, you have to use that distance formula 6 times, find out all of your lengths. Notice again, this, and this, these are all the same. So we can draw that in here. This is what our triangles look like now. So we can say, all right, awesome, look at that. These are indeed the same exact triangles. Okay, they are definitely congruent. So we can say JKL is the same as TRZ. The big ones that have to match, Z and L, are the ones that are in between the 2 tick marks. So LZ have to be the ones on the end. Okay? So those are indeed congruent triangles. All right, example 2. Tammy and John are hiking. Tammy hikes 300 feet east of the camp and then hikes 500 feet north. John hikes 500 feet west of the camp and then 300 feet north. Write a coordinate proof to prove what kind of triangle that Tammy and John and the camp make. So here we have the camp. Now they don't have necessarily any particular coordinates on here, so we can call it whatever we want. So write these in. I put the camp right at what we're going to call 0, 0. So the camp is our origin. That's where we started off at. From there, I did mine all in hundreds. So each of these boxes is 100 feet. So from the camp, Tammy went 1, 2, 300 feet east, and 1, 2, 3, 4, 500 north. Right? 300 feet east and 500 north. Same thing, Jonathan went 500 west, so this direction, 1, 2, 3, 4, 500 feet west, and up 1, 2, 300 feet north. Now, if you wanted, you could write these in as 300, 500, negative 500, 300. That would just make your distances really, really big. Let's just remember that these are all in hundreds, so we can just call them 3 and 5 and negative 5. Okay, so now we have our points, our coordinates. We wrote down, again, where each of those points is at. For this case, we're going to need to use the distance formula and our slope formula. Okay, so we'll have to find the distance between each of these and the slope to see if it makes any kind of particular triangles. So first we'll find the distance from C to J. Again, we're just plugging in our values into the distance formula. Negative 5 minus 0 squared plus 3 minus 0 squared. Negative 5 squared plus 3 squared. 25 plus 9. So we have the square root of 34, which is about 5.8. So the distance from Camp to James, right here, would be about 5.8. And remember, that's in hundreds of, we used feet, right? Hundreds of feet. So that's like 580 feet right here. Okay? So we know from the Camp to James, oops, let's do from the Camp to Tammy. Oops, get that a little bit bigger. Started at Camp, we're going over to Tammy here. 3 minus 0, 5 minus 0. 3 minus 0 is 3, 5 minus 0 is 5. 3 squared is 9, 5 squared is 25. 9 plus 25 is 34. Square root of 34 is about 5.8. So again, here to here, about 5.8, or because it's in hundreds of miles, or hundreds of feet, be about 580 feet from here to here. Okay, so that was our distance from Camp to Tammy. We need to find our distance from John, from John to Tammy, so from here to here. Again, just plugging things into the distance formula. 3 minus negative 5, and then squared. 5 minus 3, squared. 3 minus negative 5. Remember, minusing a negative is like adding, so it becomes 8. 3 plus 5 is 8. Squared is 64. 5 minus 3 is 2. 2 squared is 4. 64 plus 4 is 68. Square root of 68 is about 8.2. So in between these guys is about 8.2, or again, about 820 feet from here to here. So we have our distances. Notice that this distance is the same as this distance. So I'm going to draw that in here. Going from Camp, to Tammy, John, back to Camp. This distance is the same as this distance. We know that for sure, because over here, 5.8 and 5.8. Smartboard's getting a little off. So now we need to find their slope to see if they interact any special way. If we, move that aside. If I wanted the slope, I'm going to do JT last. I'm going to go from Camp to Tammy. So this slope right here, 5 minus 0, because I had 5 here, 0 here, so y2 minus y1 over x2 minus x1, so 3 minus 0 is 5 over 3. So that can just simply stay as 5/3. The slope from C to T is 5/3. Move that slope away. We'll do the slope from Camp to John, so from here to here. Again, y2 minus y1, so 3 minus 0 is 3. x2 minus x1, so negative 5 minus 0 is still negative 5. Positive 3 divided by a negative 5 is a negative 3/5. Remember, you're thinking of this whole fraction, this whole number, as being a negative number. So it becomes negative 3/5 is that slope. And the last one, looking at the slope from John over to, oops, move that around, from John over to Tammy. Use our y values. 5 minus 3 is 2. Use our x values. 3 minus negative 5 becomes 8. So we have 2 over 8, and that kind of makes sense. If we go from here, we have to go up 2, 1, 2, over 1, 2, 3, 4, 5, 6, 7, 8. Up 2 over 8 to get there. So our slope is 2 over 8. Or we can simplify that. 2 over 8 is the same as 1 over 4. So these are the slopes that we have for each of our sides. Okay, looking at these slopes, negative 3 over 5 and positive 5 over 3, those are opposite reciprocals. Okay, we flip our numerator and denominator, and the negative now becomes a positive. Or if we go from here to here, again, we flipped our numbers, positive became a negative. These are opposite reciprocals. If these are opposite reciprocals, that means that these two lines, oops, are perpendicular. They meet at a right angle. So if that's a right angle, and those two sides off on the edge there, those are congruent to each other, we would say then, whoops, moving the wrong thing. We would say then that JCT is an isosceles right triangle. So we've defined the kind of triangle that these three make. And that concludes section 4.